C, D, E, F, G, H, I, and we'll do some more ring counters, guys. Don't worry, we will do some more in our class. So the way, what we're going to do is we're going to do, you see, in sequential logic there is an analysis problem. Remember we did one analysis problem. There is analysis. Opposite of analysis is the circuit is given, you've asked to find the state diagram and the state table. Opposite of analysis is design. This problem is a design problem, right? So opposite of analysis is design. So we will do a design problem, all right? So this is design. So design is the other way around. The behavior of the system is given, you've got to work backwards to find what the circuit looks like. Question 2 is also a design problem. Question 2 is also a design problem, all right? Okay, question 2 is also a design problem, right? So what are we doing in class? I've done one analysis problem. I'm doing one design problem right now. I'll do another analysis problem, another design problem. So I'm going to flip-flop between the two, right? It's not that we get stuck in only analysis and stuck in only design. I want to follow one with the other so that you see it. Question 2 is another design problem, but we'll do that as well. So I'll show you this one by the end of this week, right? At least for now, you should focus on this. So my timing is, last year, students were able to solve this problem. It came in the final exam. This problem appeared in the final exam. The only difference was, instead of getting A, B, C, D, E, F, it went only till H. Went only till H. All right? So instead of 10 states, it was only 8 states. So they were able to do it in about 3 hours. It was a design, it was online exam. So we wanted everybody to have a different thing. So they were able to do it in 3 hours. So what I'm trying to tell you over here is, if you work in a smart manner, you know what's happening in your notes, you are following the lectures, sometimes students just come, I always see students are sleeping in the lectures, students are not focusing, they're going through their Facebook or TikTok or whatever it is, right? Right? But there are some students who are focusing, they're actually following. Some students are following, but they are just copying notes. They are writing down. So that's like high school level. Some students, they are copying, but they're actually exercising their mind, and they are following, questioning, why is this over here? How did they get this? So, you'll be able to do this project, problem 1 in about 3 hours, problem 2 in about 3 hours. So altogether, I've given you 3 weeks to do this problem. Week 11, week 12, and 5, all the way till end of week 13, all right? So you should be able to solve this. It's not a hard problem. Okay, and the best thing is, I'm the only lecturer who has allowed you to copy. All right, you can copy each other, you can work in groups. Okay, so these are the different unique values. So yeah, best to work in groups, figure out how to solve the problem. The method will be exactly the same for everyone. It's only a matter of you actually sitting down with pen and paper. It's going to start off with pen and paper. You've got to do it in your exercise book. How many of you started attempting it? Like, try to attempt it, right? Using whatever I've taught you. And if you want to go ahead, all my YouTube videos from last year are on Moodle Shell. You just click on the link, you can go and follow my channel, right? There's all the other courses I take are all on my YouTube channel. But if you want to go ahead and let's say I'm taking it slow over here, you're going to say, oh, Imran, it's too slow. I want to go faster. You can always watch all those YouTube videos and just finish the course this week, all right? Okay? All right. So what were we doing, guys? What were we doing? Let's move back. Let's move back. Okay, what were we doing? Right, let's start off with the design problem. Let's start off with the design problem which we were doing on Thursday evening. And we couldn't finish it because, we had spent some time on the quiz, right? So make sure you read through the thing. If there's any questions, you can always ask the question. There's 3 software which are allowed. Number 1 is Circuit Maker, that's preferred. Number 2, Logisim, if you wish. Number 3, Quarters. There's another software in the lab, it's called Quarters, right? All right, now, okay, let's go to the document camera. Let's have a look at this problem. So now you realize that the reason why I did one analysis problem, and I jumped to this design problem. So in this particular design problem, there's only 3 states, A, B, C, and then returns back to A. So this is actually your project problem number 1. This here is project problem number 1, but a miniaturized version, right? Okay, it's a miniaturized version. Okay, so it's like I'm teaching you in this problem here how to ride a tricycle, but in the end you have to ride a bicycle, right? Okay, slightly different dynamics, but you get the idea of how to pedal at least, right? Pedal and steer, right? So this here is the same identical problem. This problem here, which we started last week Thursday, is absolutely identical to our project problem number 1. So that's 35 marks in the bag, right? Of course, from the report, everyone can score 30 out of 30, right? 35 marks out of, so problem 1, 35 out of 35, except for over here we're only doing A, B, C, and in that one there we're doing A, B, C, D, E, F, G, H, I, right? So only the mode of the size of the problem has changed. All right, so, okay, so from there, this was the original problem. If it's x equals 0, it goes in this direction. If x equals 1, it goes in that direction. And this was given. This was part of the question. Part of the question was, so let me separate this. This is part of the question, that A is 3, B is 1, C is 0. And then I redrew this into like a circle, right, so that you see the ring. That's why we call it the ring counter, right? They call it the ring counter. X equals 0, x equals 1 in that direction. These are the values. Then we redrew it in a proper state diagram. Then we changed the state diagram to binary. Then we accounted for the unused states. So guys, if you did not attend last week Thursday's lecture, but I do presume everybody attended because there was a quiz, right? Then from that state diagram, we went to the state table. From the state table, we started doing the Kano maps. So let's finish it off, guys. Let's finish this particular problem off. Okay, let's finish off this problem. So, today's date is from here. Okay. So what we're going to do? KB. So we want to now, from this here, we were able to develop the state table, right? And you must attend lectures. If you miss out a lecture, you are in trouble. All right. From the state table, we extract for each of these flip-flop inputs, we extract the equations. So we've done JB, let's do KB. Okay, let's do KB. Okay. Let's do this, guys. 0, 0, 0 will give you, KB is x. And 0, 0, 1 is also x. 0, 0, 0 is x. 0, 0, 1, 0, 0, 1 is also x. Okay, let's look at the next one. 0, 1, 0 is 0. 0, 1, 1 is 1. 0, 1, 1 is 1. So 0, 1. 0, 1, 0 is 0, 0, 1, 1 is 1. All right? Now, next. 1, 0, 0 is x. 1, 0, 0, 1 is also x. 1, 0, 0 is x. 1, 0, 1 is also x. Okay, fine. Everybody happy with that? Okay. Next one. Last two. 1, 1, 0 is 0. 1, 1, 1 is 1. 1, 1, 0, 0. 1, 1, 1 is 1. So we've got to plot. What are we going to do? We've got to make a group. Okay, so we make a group. There we are. So that's the best possible group. And therefore we can say that KB is equal to, what can we say, guys? KB is equal to Yeah, QA. All right, now let's look at JA. Let's do a Kano map for JA. It's 1x, 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 right? So you should, by now, so what are we doing, guys? See, you develop the state table, right? Where did the state table come from? So once again, for those of you who have just arrived, we have this problem. This was the question. That goes this way. And we were given that A is equal to, so we were given that, hey, A is equal to 3, B is equal to 1, C is equal to 0. We redrew this in this particular manner. Then we redrew that by filling in the information, right, in a state diagram method. Then we converted the state diagram to binary, and we realized, hey, there's an unused state. How do we know there's an unused state? Well, if there's 2 flip-flops, the largest number was 3, so therefore 2 bits required. 2 to the power of 2 means there's 4 flip-flops. So, 4 states, right? So, 2 to the power of 2 is 4 states. Only 3 were occupied. 3 occupied. Therefore, 1 unused. Right? Therefore, 1 unused. All right? So we found that that's the unused state. We redrew it in binary. From the binary state diagram, we went to the state table. From the state table, we now want to get the equations for each of the flip-flop inputs. So for JA, it's 1x, 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 1x. All right. So that's easy to remember. So if everything is 1x, 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 1x. Right? Okay, if you know, by now you should be familiar with how the Kano map, which cell number is where. All right? That should be the back of your head. So we now realize, hey, that's another loop. And we can say that JA is equal to, actually, let's, oh, I made a mistake there. Can somebody tell me what's my mistake? Let's look at that Kano map for JA. I made a mistake. I went too fast, and that's another thing which you learn over here. If you go too fast, you can make a mistake. What is the mistake I've made on that Kano map? This is like a week 3 mistake. Week 5 mistake. Something which you did in week 5 or week 6. Yeah? You see, when do we use the X? To make a larger group. Can we use the X? Yes. We can use the X. That's our group. Right? The whole thing is grouped. So, if the whole thing is grouped, we just say 1. All right, now let's look at KA, JA. Oh, guys, this should be KB. Sorry, KA, right? JA, KA. Right, okay. Right, so once again we go to the state table. X1, X0. Okay, let's do this. X1, X0. X1, X0. So the next one is X0, X1. When you start from that side, it will start from here. X0, X1. Do you guys realize why I went outside then inside again? Yeah? You follow that through. Okay, now. Over here, in this particular scenario, okay, there's only one option over here and one option over here, right? KA would equal to X bar, QB bar, or X QB. Yeah, everyone in agreement with me? Is everyone in agreement with me? All right, now, from there, what's the next step, guys? That's not the end. Final step. So everyone seen how, is everyone okay with how I got to this stage? How I got the 4 formulas? You see, when we do analysis, you start off with a circuit. Somebody will give you a circuit. From the circuit, what did we do? Like in the quiz, we found the equations. From those equations, we plug it into the state table. Of course, some parts of the state table are done automatically, like the input, output, depending on what the diagram looks like, what the circuit diagram looks like. Then from the state table, we go to the state diagram, right? And from the state diagram, we can talk about the behavior of the, you can put like a small paragraph in English language about how that particular circuit is behaving, right? Okay? Now, that's analysis in that direction, right? Now, what about design? Design, somebody gives you the behavior. This is what I want the circuit to be. I want the circuit to produce even numbers on every clock cycle, 2, 4, 6, 8, 10, right? Okay? So from there, we draw the state diagram. From the state, first we will draw the state diagram in normal decimal numbers, 2, 4, 6, 8, 10. If x equals 0, if x equals 1, it goes the other direction, right? From the state diagram, we go to the state table, right? From the state table, we extract the formulas for the flip-flop inputs, the algebraic equations. From there, we draw the circuit. Well, if you have got the hardware option, then from drawing the circuit diagram on paper, you implement on hardware. Okay, so that's the process. One is in one direction, one is in the other direction, right? And we'll do problems of both directions. So I'll mix it up. Sometimes I'll do analysis problems, sometimes I'll do those problems. So we are on the third step, final step. Step 4 is the circuit. Right? And today's date, guys, is, what's today's date? June 7th. And this is week 11, lecture 1. All right. Now, tell me, by this part here, that was the state diagram, what did we learn over here? The largest number in our system was 3. Yeah? How did we get 3? That was part of the problem. The largest number was 3. So 3 in binary is 1, 1. And 1, 1 requires how many bits? That means it's 2-bit system. So therefore, how many flip-flops? 2 flip-flops. 2 flip-flop means how many possible states? 4 possible states. So though all these little bits of information helps. The 2 flip-flops, we will draw that in our circuit right now. What sort of flip-flop is required? What flip-flop was asked of us in the question paper, in the question? It says use JK. So we're going to use JK. All right? 4 possible states, where does that come in? To find the unused state and so forth. All right? And state diagram and so forth. All right. So what was it? JK flip-flop. So all of it is in the same question. So let's do the 2 JK flip-flops. Right. So we draw the circuit. 1. By the way, guys, those of you who are doing CS211, are you doing design and all that? Did you go deep into flip-flops? No? Okay, all right. Okay. So, JA, KA, JB, KB, QA, QA bar, QB, QB bar. Sorry, there's no bar over there. QB, QB bar. All right? Okay. I think I'll start off with with the easiest part. The clocks are always the clock line is always synchronized. Okay, the clock line is always synchronized. Okay, everyone happy with that so far? Let me zoom out slightly so that you can see the whole circuit. So I'm doing the circuit now. All right, let's see. Let's look at our equations. Okay, JA equals 1. All right, nice. JA equals 1. I'll just put a 1 over there. Set? Everyone happy with that? All right, now next one. KB is equal to QA. KB is equal to QA. So from here, there, can you see I've connected it that way? Set? Yeah, everyone happy with that? KB is equals to QA. So I've taken care of two inputs. Let's now look at the two hard inputs. This one here, let's look at JB. There's got an X and X bar. So we have to start with an X. So we start with an X. X comes down this way. And there will be a line for X. Okay, and there will be a line for X bar. So obviously that becomes X bar over there, right? Okay, and what was this guy equal to? X bar, QA bar, X, QA. Wow, all right. QA and QA bar, right? And that goes into, what was it? JB. So for JB, there'll be an OR gate. Guys, I'm drawing this by hand right now, but obviously when you do your projects and labs and all this, you always in real life use software. Eh? I'm just teaching you, well, you know, what. Okay, and these two are fed with two AND gates. One is X bar and QA bar, yeah? X bar and QA bar. That's X bar. Oh, no. This here is QA bar. So let's just check it. That over there is X bar. What's over here? That's QA bar, right? What's the other one, guys? X and QA. Oh, nice. So we have X and QA. So maybe I'll take this guy over here. X. Sorry, that's QA. So that'll be our X, that'll be our QA. Set? Okay? It's slightly messy because I'm drawing it using hand and no pencil. So I always advise students to use a pencil. All right, so which ones are done? Let's see. I've done this. Yeah? I've done this. I've done this. Last one. X bar, QB bar, X, QB. Okay. And that is equal to what, guys? KA. All right, so KA is over here. So we'll put a nice OR gate. And we have two AND gates. What does it say? X bar, oh sorry, you're down here. X bar, QB bar, X, QB. Okay, QB is right over here. QB is right over there. So what do we do? So that's our QB. X. Oh yeah, this guy here is X, right? Nice, just lines up just like that. The next one was X bar, right? Yeah. So this is X. This is X bar. Right? What about this? One more left. What was it, guys? What was the last line? QB bar, right? All right, that's your circuit. Then you may be asking, well, then where's the output going to be? The output is always along the QA and QB, the main, not the inverted one. So you will connect two LEDs over here. You'll connect an LED to QA and connect an LED to QB. And then in that cycle, when X is equal to, there's an X over there as well. When X is equal to 0, it will go A, B, C cycle, like what we've drawn in the question. What is it, 0, 1, 3 or something? Or 0, 3, 1. And when it's in X is equal to 0, it will go the other way, right? So it will flip. The lights will go 0, 0, 0, 1, 1, 0. It will light on, double off, 1 on, 1 off. Okay, according to that. So you'll connect LEDs to your QA and QB. Right? Okay? So that's how you draw that circuit. So that's a circuit. In fact, this exercise doesn't carry much marks, the drawing part. Because the hard part, the technical part, anybody can draw a circuit. Right? The hard part is designing the circuit, which you had to do using your, the state table, state diagram, state table, and getting the equations from the Carnot maps. Okay. Any questions? All right, let's do another problem, guys. So let's flip over. I would like to do one of these problems. So let's go back to analysis now. So this is how it's going to be. We're going to flip between analysis. We're going to flip between analysis and so one round we'll do analysis. We'll do one design. One analysis, one design. All right? Okay. So let's do analysis problem. So guys, everybody should have received one of these, right? If you did not receive one of these, that means you were missing from at least, well, all 3 of last week's lectures, right? Which puts you in trouble. Okay. So the purpose I've given you this is so that we can move faster. So we're going to do our analysis problem. Problem 1. Okay. Let me zoom in. So guys, we are changing the nature of the program, okay? I mean, nature of the problem now. And I'm deliberately doing this so that you guys can see that, hey, everything is linked together. You don't separate in your mind, right? And right now, you are ready to go with project question number 1. Work in groups, guys. Work in groups, okay? Work in groups so that you can score bigger mark. I'm not here to fail you. I'm just here to challenge you, right? I'm just here to challenge you. I don't want to fail you. I want to challenge you so that you become a better engineer, all right? Okay, now, let's have a look at this problem. Now, step 1. Step 1 is what? Step 1 is we want to find okay, firstly we recognize how many flip-flops? How many flip-flops, guys? In question number 1. 2. Bring this paper out if you have it. If you don't have it, you can draw it in your exercise book, right? I've run out of all of this, right? There are 2 flip-flops, so therefore it's a 2-bit system. So take note of this. There are 2 flip-flops. Each flip-flop can only store 1 bit at any point in time. If there are 2 flip-flops, obviously it's a 2-bit system. If it's a 2-bit system, there are only 4 possible states. 0, 0, 0, 1, 1, 0, 1, 1. All that will come useful in the state diagram later on, right? The type of flip-flop we are using is D flip-flop. D flip-flop. Sometimes, hey, over here I've labeled it DA, DB. Sometimes they label it Q1, Q2. Sometimes they call it Q, you know, Q triangle, Q square, Q cross, Q circle, right? Whatever it is, okay? So you have over here 2 flip-flops. So I think we started off well. Now, D flip-flops, each flip-flop is only one input. So therefore we need to find, step 1 is find the equations for the flip-flop inputs. And this is what we did in the, not the same question, the question in the quiz was different. The question in the quiz was heavy duty, something like this, right? Okay, this is an easier problem. Okay, so let's find the equation. What will dA equal to? So if you go over here, that's x end QA, what do you have, guys? X end what do you find? What can you tell me? You have x so over here we have x and QA going into that OR gate. Goes there. That's x. What's about the other one, guys? What's the other one? QB. So that's x and QA or QB. So we can say that dA is equals to OQB. All right. Now, let's look at this one here. What's this, guys? If that's QA, no, this line here. Look at this line. That is QA. You have to follow the line. That becomes QA bar, right? What about this line here? That's coming in from QB. So that's QA bar and QB. So what can we say about dB? dB is equals to QA bar and QB. By the way, guys, if you don't have a copy of this, or if you've lost your copy, or if your dog ate your copy, you can find this on the Moodle shell. I've loaded it onto the Moodle shell. All right, so we found our equations. Nice. We have found our equations. We have found our equations. Okay, now, the next problem. In the next problem, we have we now move to the next step. So step 1, I did it right on the circuit. Right? So let's go write that down. Step 2 is, so that was step 1. This is an analysis exercise. Step 2 is the state table. Sorry? Oh yeah, sorry. There is one guy left out. I forgot about him. Right, there's a Y over here. System output, Y. Okay, let's do this. So there will be QA and, what will that be, guys? So if that here is QA, what is this guy here? X. So this becomes X and QA. What about this guy here? That will become X bar. What about this guy here? QB bar. So your Y will equal to X and QA or X bar and QB bar. Right? Yes, thank you. I totally missed that out. Right? So over here, your particular your dA, sorry, your Y will equal to X and QA or X bar and QB bar. By the way, guys, one of these questions is repeated in the tutorial, if I'm correct, or different? Different, right? Okay, that's good. Okay, state table. Let's draw our state table. Let us draw our state table, which isn't too much of a hassle, by the way. Do not get scared by these big names. So state table, you have X. It really doesn't matter what order you write it in, so long as you're consistent. QA, QB. Then there's DA, DB. Then there is QA star, or some people call it QA n plus 1. QB star. Then there is Y. Okay, so this is the system input. This is the current state. This is the flip-flop inputs. This is the next state. This is the system output. Okay, now how do we populate this side? So over here, these three lines these three over here give us the input section, these three. So we populate, so I'll use black. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Yeah? So that part was easy. You just flow with whatever is available. All right, now, I mean the possible number of combinations, because there's only 3 over here. Right, the next part. Let's look at DA. Now DA, we've got the formula. Right, so let's put it all on one page. We have the formula. Okay. Set. We don't need to look at the circuit anymore because we've got the equations, placed in there. Bang. Done. Right. We have the formula. All right. Now DA. What is DA equal to, guys? Can you help me out over here to calculate DA? So maybe this side of the house, this left-hand side, will do DA. The right-hand side will do DB. Okay. Right, and then we'll do Y together. If you guys can go ahead and find the answer, you can, it'll be good. Right, talk with your neighbor. If you can find for Y, everyone can do Y together. Right, DA on this side, DB on this side. All right, how does it look, guys? So DA, is it ready? DA, let's go ahead with DA. So 0, 0, 0, DA would be 0. Yeah, if anybody got a different answer, let us know, right? 0, 0, 1, 1. 0, 1, 0, 0. 0, 1, 1, 1. 1, 0, 0, 0. 1, 0, 1, 1. 1, 1, 0, 1. 1, 1. Anybody got a different answer? So you've got 0, 1, 0, 1, 0, 1, 1. All right, let's do DB. So somebody from there, you call out DB. 0, 0, 0. 0, 0, 0, DB. 0, okay, 0, 0, 1. 1. 1, 0, 1, 0. 0. 0, double 1. 0. 1, double 0. 0. 1, 0, 1. 1. 1, 1, 0. 0, 1, 1. So you got 0, 1, 0, 0, 1, double 0. Yeah, anybody got something different? All right, okay, let's look at Y. So straight away we can do all the flip-flop inputs and system output. What is Y, guys? What is Y? Y, okay, 0, 0, Y. All right, I give you guys 1 more minute. Let's sort out Y. Somebody got 0, 0, you got Y of 1, is that correct? 0, 0, 1. Come on, guys, what do we have? 0, 0, 1, 0. 0, 1, 0? Sorry? 0. Right. 0, double 1? Come on, guys, we've got not much time. 0, double 1? 0? Yeah? 1, double 0? 1, 0, 1? 0, 1, 1, 0. 1. 1, 1. Is everyone in agreement with me, or is there some mistake? Yeah, okay, tell me which line. 0, 1, 0. Can we check 0, 1, 0 for Y, please? 0, 1, 0 for Y. What do we get? Okay, we get a 1. Yeah, so 0, 1, 0 in Y, we get a 1. All right, now, so do you see, look at this. 3 columns, these 3 columns, they got filled out automatically because they're on the input side. So you just fill it out according to all the possible combinations. These 3 columns, they got filled out by the formula. What do you have left? Just those 2 columns. How are we going to fill them out? We have to use the tables. So which table are we going to use now, guys? We know your current state. We know your current inputs. You want to predict what will be your next state. So what are you going to use? Characteristic table. So let's have a look at this. Right? In the characteristic table, Q star is equal to D. So your next state is your current input, yeah? You look over here, you see this table. By the way, for those of you who missed out on Thursday's lecture, there is an omission over here. You have to add these 2 to the D excitation table. All right? Now, we are using the D table, the characteristic table. So if you look at the column of the Q star and the D, they are the same. Yeah? So what we can do is say QA is equal to same thing, DA, yeah. 0, 1, 0, 1, 0, 1, 1. And QB is 0, 1, 0, 0, 1, double 0. So whenever you get a D flip-flop problem, that's like a gift problem. You know why? Because your next state is identical to your current flip-flop input. No issues at all. All right? Okay, one more step, guys. So that was step 2. Step 3 is the state diagram. All right, so let's do the state diagram. Now, how many flip-flops are there in our question? How many flip-flops are there? There are 2 flip-flops. So how many possible states will there be? 4 possible states. All right, so 4 possible states will be 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 possible states. All right? Okay, even if sometimes a state in the design problem, one possible state is not shown, right? It's called an unused state, like what we did in our design problem. That's common in design. But in analysis, no, we don't have that problem. In analysis, we don't call it an unused state. All right, now, so let's look at this, guys. QA is 0, 0, and the next state is, if x is equal to 0, right, where does it go? It goes to itself, right? Stays the same place. QA and QB, 0, 0, remain at 0, 0 if x equals 0. So what you're going to do is, if you have a ruler, you know, you go line by line, something along those lines, all right? 0, 0, right, remains at 0, 0 if x equals 0, but y becomes 1. So it remains at the same place, right? If x equals 0, but y becomes 1. All right, okay, next one. Let's look at the next line. 0, 1 becomes 1, 1. Yeah, 0, 1 becomes 1, 1. 0, 1 becomes 1, 1. And what was x? X was 0, y is 0. You put it like that. Yeah, everyone happy? Third line. 1, 0 becomes what? 0, 0. 1, 0 becomes 0, 0. 1, 0 becomes 0, 0. And what can we say about x and y? 0/1, right? Okay. Now 1, 1 becomes 1, 0. 1, 1 becomes 1, 0. 1, 1 becomes 1, 0. What can we say about x and y? They're both 0. 0, 0 stays at 0, 0. We got that one again. See? 0, 0 stays at 0, 0. And what are the conditions? The conditions is x is equals to 1, y is 0. So you see this one here? So we say 1, 0. So we put 2 lines there. So 0, 0 stays at 0, 0. We don't have to redraw this. We just put the additional condition over there. All right. 0, 1 becomes 1, 1. 0, 1. Hey, 0, 1 becomes 1, 1. Again, another one over here. 0, 1 becomes 1, 1. This time the conditions are 1, 0. 2 conditions. All right. 1, 0 stays at 1, 0. 1, 0 stays at 1, 0. 1, 0 stays at 1, 0. The conditions is x is 1, y is 1. 1, 1 becomes 1, 0. 1, 1 becomes 1, 0. 1, 1 becomes 1, 0 going down that way. And what are the conditions? It's 1, 1. That's it. That's your state diagram.